Energy levels. Here the uh, different energy level of electrons is shown. The lowest level is for n equals to 1, and this is called ground state lowest energy, and its value is minus 13.6 electron volt. And this is the first excited state, and in this, in the second orbit, this is the energy equals to minus E2 equals to minus 3.4 electron volt. Similarly, 3 is minus 1.51 electron volt, and similarly we go above, and this is the unbound atom state where energy becomes zero. That is, atom becomes ionized. Now electrons is free from the atom. In this case, when energy becomes zero, electrons is free from nucleus, and these are all, and other states are bound state because electrons are bounded to the orbit. The energy of a hydrogen atom in nth orbit or nth state is given by n equals to minus 13.6 by n square electron volt. When n equals to 1, that is, the electron is revolving in innermost orbit, the energy of H atom is E1 equals to minus 13.6 electron volt, which is lowest. This state of atom is called ground state. Second, in other orbit n equals to 2, n equals to 3 etc., the energy of H atom is higher and is called excited state of H atom, or E2 equals to minus 3.40 first excited state, E3 equals to minus 1.51 second excited state energy, etc. Third, when n equals to infinity, infinity becomes zero. That energy in infinite orbit becomes zero. That is, the H atom has maximum energy. In this case, electron is free from hydrogen nucleus. This is called unbound state or ionized state of hydrogen atom. So the minimum energy required to free the electrons from ground state of H atom is 13.6 electron volt. This is called the ionization energy of the H atom. At room temperature, most of H atom is in ground state. The line spectra of hydrogen atom. According to the third postulate of Bhors model, when atom makes transition from one state to another state, the photon is observed or emitted having energy equal to h nu if equals to ei minus f equals to eni minus enf equals to minus 1 by ni square mu to the power 4 by 8 epsilon naught h square minus or minus 1 by nf square me to the power 4 8 epsilon naught h square equals to m into e to the power 4 by 8 epsilon naught h square under bracket 1 by nf square minus 1 by ni square. This implies h nu if equals to m into e to the power 4 8 epsilon naught h square 1 by nf square minus 1 by ni square. So nu if or nu equals to m into e to the power 4 by 8 epsilon naught h cube 1 by nf square minus 1 by ni square, equation 1. This is called Rydberg formula for the spectrum of hydrogen atom. If we take nf equals to 2 and ni equals to 3, 4, 5, it reduces to the form similar to formula for Balmer series and given by nu if equal to m into e to the power 4 8 epsilon naught h cube 1 by 2 square minus 1 by ni square, where ni equal to 3, 4, 5 etc. That is, electron is jumping from third orbit, fourth orbit, 5 orbit to the second orbit, and then energy released in this case is this. This is the frequency of energy. Or C by lambda if equals to m into e to the power 4 8 epsilon naught square h cube 1 by 2 square minus 1 by ni square, or 1 by lambda if equals to m into e to the power 4 8 epsilon naught square h cube into c 1 by 2 square minus 1 by ni square. So Rydberg constant R is identified as R equals to m into e to the power 4 8 epsilon naught square hq into c equal to 1.03 into 10 to the power 7 per meter. This is very close to the value 1.09 into 10 to the power 7 per meter obtained from the empirical Balmer formula. This agreement between the theoretical and experimental values of the Rydberg constant provided a direct striking confirmation of Bohr's model. Now, if Ni is greater than Nf, that is, electron jumps from higher energy state to lower energy state, photon is emitted and we find emission line spectra. Example, Ni is equal to 3 and Nf equals to 1. Second, if Nf is greater than Ni, that is, electron goes from lower energy state to higher energy state, then photon is observed and we find observation line, that is, for example, Ni is equal to 2 and Nf equals to 5. That is from second orbit to the third orbit, fifth orbit, that is, electron is jumping from second orbit to fifth orbit. So energy will be observed. Different series is shown in terms of electron energy or orbit energy. Uh, this is the ground state of hydrogen atom, that is E1 is equal to 13.6 electron volt. This is the ground state of state. If any electron jumping from higher state, that is from n is equal to 2, n is equal to 4, n is equal to 3, if jumps on the first orbit, then this will Lyman series will be formed. Similarly, if on second orbit other electron higher than second orbit will jump, then Balmer series will form. Similarly, third orbit, if electron jumps on third orbit, then Paschen series will form, and bracket series will be formed similarly, and finally a ionized atom state will be achieved when the energy of orbit becomes 0. Now de Broglie's explanation of Bohr's second postulate of quantization. De Broglie established a connection between the wave nature of electrons and stable orbits in Bohr's model of atom. He assumed that an electron orbit would be stable only if it contained an integral multiple of electron wavelength. That is, the circumference of the orbit should be equal to the integral multiple of wavelength. This is shown, this is lambda, and the orbit is shown by this wavelength. Third orbit, this is second orbit, 2 lambda, and this is first orbit, 1 lambda. Here wave is assumed as a standing wave. From this assumption, we have 2 pi r equals to n lambda, where n equals to 1, 2, 3. From Bohr's postulates of quantization of angular momentum, L equals to n into h by 2 pi. This implies mv r equals to nh by 2 pi, or 2 pi r equals to nh by mv, or 2 pi r equals to n into h by p equals to n lambda. Hence 2 pi r is equals to n lambda. Thus the circumference of the orbit of an electron is equal to the integral multiple of the de Broglie wavelength of the electron moving in the orbit. Next, drawbacks of Bohr's atomic model. First, this model could not explain the spectra of complex atom having more than one electron. To when the spectral lines of a Balmer series was observed under a powerful microscope, it was found that each spectral line consists of closely spaced lines. Bohr's model could not explain this fine structure of the spectral lines of Balmer series. Third, this model does not give any idea about the relative intensities of the spectral lines So we could not explain the splitting of spectral lines into a number of spectral lines under the effect of magnetic demand. Now the nucleus. The idea of nucleus was first introduced by Rutherford on the observation of his alpha scattering experiment. According to him, almost mass of the atom and positive charge is concentrated in a small spherical volume at the center of the atom and is called nucleus. Now properties of nucleus. Properties of composition. Properties of nucleus, that is first is composition. All nuclei are composed of two types of particles, protons and neutrons. These are also called nucleons. Mass of proton 1.6726 into 10 to the power minus 27 kg and mass of neutron 1.6750 into 10 to the minus 27 kg. Now atomic number Z is equal to the number of protons and mass number A equal to the number of protons and neutrons. Neutron number is represented by n equals to number of neutrons. Thus A equals to Z plus n, that is mass number is equal to number of protons plus number of neutrons. Now symbol of nucleus is represented by ZXA or ZXA, where Z represents the atomic number, A is represent the mass number. For example, 39 AU 197, 79 AU 197 and 29 CU 64. That is 29 represents the atomic Z, that is atomic number, and 64 represent mass number. Similarly, in this 79 represent atomic number and 197 represent mass number. The types of nuclei. First, isotopes. Nuclei having the same atomic number, that is Z, but different n and a values are called isotopes, that is but different neutrons number and mass number, then will be called isotopes. That is, for example, isotopes of hydrogen 1H1, 1H2, 1H3. The Z number is same for 3 and mass number is different. Here Z is equal to 1 and A equal to 1, 2, 3. So this is isotopes, and this is called hydrogen, this is called deuterium, and this is called tritium. Again, isotopes of carbon is 6C11, 6C12, 6C13 and 6C14. 6C11 is found 1% and 6C that is 6C12 is found mostly 98.9%. Gold has 32 isotopes. Now also bars. Nuclides, that is nuclei of different elements having the same mass number value but different atomic number and number of neutron values are called isobars. For example, 1H3 and 2H3, because these two elements have same mass number but different atomic numbers. Similarly, 6C14 and 7N14, these have same mass number and different atomic numbers, so these are called isobars. Now isotones, nuclides having the same n value but different A and Z values are called isotones. In 1H3 and 2H4, here A equals to 3, Z equals to 1 and N equals to A minus Z equals to 2. And similarly in 2H4, A equals to 4, Z equal to 2. So N equals to A minus Z for minus 2. So both have same number of neutrons. So these two nucleides will be called isotones. Similarly, in this case, 8O16 and 6C14. Here A equals to 16 and Z is equal to 8 and N equals to A minus Z, 60 minus Z equal to A, and similarly A equal to 14 and Z equal to 6 and N equals to A minus Z, 14 minus 6 equals to 8. So these two nuclei are also isotones. Now size of the nucleus. The size of the nucleus is of the order of femtometer, which is also called Fermi, or 1 femtometer or 1 Fermi is equal to 10 to the power minus 15 meter. Most nuclei are almost spherical with an average radius r given by r equals to r naught into a to the power 1 by 3, where a is the mass number and r naught is equivalent to 1.2 into 10 to the power minus 15 meter. Now atomic mass unit AMU. In 1960, carbon 6C12 has been accepted internationally as the reference of atomic mass unit. One atomic mass unit is taken as the 1 by 12th mass of 6C12 atom. The mass of one 6C12 atom equals to 12 gram by 6.023 into 10 to the power 23, or 1 AMU 1 by 12 into 12 by 6.023 into 10 to the power 23. This implies 1 AMU equals to 1.66053 into 10 to the power minus 27 kg. So 1 AMU or 1 U is equivalent to this mass. Now mass energy equivalence. According to Einstein, mass can be converted into energy by E equals to m into c square, where c is the velocity of light in vacuum. This energy is called mass energy. Thus, energy equivalent of 1 AMU mass is 1.6 into 10 to the minus 27 into 3 into 10 to the power square equals to 1.49 into 10 to the power minus 10 joule, equals to 1.49 10 to the power minus 10 divided by 1.6 into 10 to the power minus 13 mega electron volt, or 1 AMU equals to 931 mega electron volt, because 1 electron volt 1.6 into 10 to the power 19 joule and 1 mega electron 10 to the power 6 into 1.6 into 10 to the power 19 joule equals to 1.6 into 10 to the power 13 joule.